There is a story we tell ourselves about the cosmos, and it is a comforting one. We imagine the universe waking into existence and then waiting, patiently and purposefully, through the long dark ages of deep time, arranging matter and energy in careful, deliberate strokes until at last, after 13.8 billion years of cosmic labor, it produced us. We imagine ourselves as the destination. We imagine the universe as a patient craftsman who always knew what the finished product would look like. That story is wrong in every physical detail, and the true story is far more staggering. The universe did not wait for us. The universe does not wait for anything. It does not plan, it does not select, it does not prefer. It is a blind, churning furnace governed entirely by the impartial arithmetic of quantum mechanics and thermodynamics, and the only reason we exist at all is that those equations, when given sufficient time, will occasionally and incidentally produce structures of breathtaking complexity as a simple statistical byproduct of their relentless operation. 13.8 billion years is not a long delay. It is the bare minimum. It is the unavoidable physical price of our existence, not measured in patience but in thermodynamic necessity. To understand why that price is so steep, consider an analogy on a cosmic scale. Imagine a mechanical clock so vast that its gears span an entire galaxy. The gears are not designed by any watchmaker. They were assembled by random physical processes, by the gravitational collapse of dust clouds, by the blind churning of stellar winds, by the slow crystallization of matter across incomprehensible distances. The clock ticks. It has always ticked, but the gears do not turn with purpose. They turn because angular momentum and gravity and friction compel them to turn, and each revolution is entirely indifferent to its own outcome. Now imagine that somewhere inside this galaxy-sized machine, there is a single sequence of microscopic gears, 10,000 of them, that must align in precisely the correct geometric relationship for a certain kind of molecular chemistry to become self-sustaining. The clock does not know this alignment is possible. The clock does not care. It simply ticks, one blind revolution after another, through trillions of configurations that produce nothing of note, and the overwhelming majority of those configurations are dead arrangements that dissolve and reset without consequence. But after an almost incomprehensible number of ticks, after the kind of waiting that reduces ordinary human time to a rounding error, those 10,000 microscopic gears finally find each other. That is not destiny. That is statistics operating on an almost unimaginable timescale. We are those microscopic gears, and the clock started ticking 13.8 billion years ago. The first chapter of this story is written in the cold arithmetic of the early cosmos. When the universe was young, a fraction of a second old, it was a plasma of extraordinary temperature and simplicity. Quarks bound into protons and neutrons, and within the first 3 minutes, those protons and neutrons fused into the lightest atomic nuclei: hydrogen, helium, trace quantities of lithium. That was essentially the entire chemical inventory of the infant universe, a vast and featureless ocean of the two simplest elements, cooling and expanding into the dark. Think carefully about what is absent from that list. There is no carbon, there is no oxygen, there is no nitrogen, no phosphorus, no sulfur, no iron. Every element that biology requires in any meaningful quantity, every atom that participates in the construction of a protein, a membrane, a nervous system, a brain capable of asking the question we are currently exploring, none of it existed. The early universe was chemically destitute in precisely the way that matters for life. It was a cosmos that could not, in any physical sense, produce conscious observers, not because it lacked time, but because it lacked the atoms. The only factory in the universe capable of producing heavy elements is the core of a massive star. Stellar nucleosynthesis is one of the most beautiful and violent processes in nature. When a star of sufficient mass collapses under gravity and ignites its hydrogen fuel, it begins a progression of nuclear burning that climbs the periodic table with each successive phase. Hydrogen fuses to helium. Helium fuses to carbon and oxygen. Carbon burns to neon, neon to oxygen, oxygen to silicon, silicon to iron. Each step requires higher temperatures and higher pressures, and each step releases less energy per reaction until the iron core can no longer sustain fusion. and the entire stellar structure collapses catastrophically in a fraction of a second, rebounding in a supernova explosion of almost incomprehensible luminosity. That explosion does two critical things. It synthesizes the heaviest elements in the universe, those beyond iron, through rapid neutron capture in the final violent seconds of stellar death. And it disperses all of these hard-won elements across enormous volumes of interstellar space, seeding the void with carbon, oxygen, silicon, iron, and dozens of other atomic species that had never before existed anywhere in the cosmos. But here is the part that dismantles the comfortable story even further. The first generation of massive stars, the population that formed from pure hydrogen and helium in the early universe, had to live out their entire lifetimes and die before any of this enrichment could begin. The most massive stars burn fast and bright, exhausting their fuel in as little as a few million years. But the dispersal of their remains, the mixing of their ash back into the interstellar medium, the slow gravitational recollection of that enriched gas into new stellar nurseries, these are processes that operate on timescales of hundreds of millions to billions of years. The universe needed time not because it was being careful, but because the physics of stellar evolution and interstellar mixing operates on timescales that dwarf all of human history repeated millions of times over. We are the ash of stars that died long before our sun was born. That sentence is not poetry. It is chemical accounting. The second chapter of this story is written in the physics of planetary formation, and it introduces a threshold so demanding that most of the universe will never cross it. Rocky planets, the kind capable of holding liquid water at their surfaces, are not simply compressed balls of generic matter. They are the product of a specific minimum concentration of heavy elements in the protostellar disk from which they form. Astronomers call this the metallicity threshold, the minimum abundance of elements heavier than hydrogen and helium that a stellar system must possess before it can condense stable, differentiated, rocky worlds. The physics here is unforgiving. Light elements dominate the early universe, and a protoplanetary disk composed primarily of hydrogen and helium will not produce a silicate mantle or an iron core. It will produce gas giants and ice bodies and diffuse clouds that never consolidate into the kind of chemically complex solid surface where liquid water can persist. To build a world like Earth, you need repeated generations of stellar birth and death, each cycle enriching the interstellar medium a little further, slowly accumulating the chemical complexity required for rocky planetary geology. Our own solar system formed roughly 4.6 billion years ago from a cloud of gas and dust that was itself the product of multiple prior stellar generations. The Sun is not a first-generation star. It is a late-generation star, formed from material that had been processed through the cores of earlier stars and expelled in their deaths. The heavy elements in Earth, the silicon in its mantle, the iron in its core, the oxygen in its water, these atoms were forged in stars that preceded our sun by billions of years. We did not simply need time to form. We needed the universe to run enough stellar cycles to produce the raw materials from which we could be built. And even after a rocky, water-bearing planet forms, the story has only just begun. The third chapter is written in the uncompromising language of the second law of thermodynamics, and it is perhaps the most humbling of all. Life, at its physical core, is a process of maintaining local low entropy in the face of a universe that relentlessly increases in entropy overall. A living cell is a thermodynamically improbable arrangement of atoms, one that continuously consumes energy to sustain its structural complexity against the constant statistical pressure toward disorder. Building that complexity from simple chemistry is not a guided process. It is a random walk through an astronomically vast space of possible molecular configurations driven by the differential reproductive success of structures that happen to be slightly better at persisting and replicating. This is not a gentle or rapid process. The fossil record and molecular clock analysis both confirm that life on Earth spent roughly the first 3 billion years of its existence as single-celled microorganisms, spending the vast majority of biological time not climbing toward complexity, but simply surviving at the most basic level of cellular organization. The transition to multicellular life, and then to nervous systems, and then to the kind of neural architecture capable of modeling the external world in sufficient detail to generate conscious experience, these transitions required not just time, but an extraordinarily stable and long-lived energy source radiating at the correct wavelength to drive photosynthesis and sustain a planetary climate within the narrow thermal window where liquid water and complex chemistry are simultaneously possible. That energy source is a star of precisely the right mass and stability to burn for billions of years without dramatic variability. Our sun is that star, but even given that stable energy source, the blind and grinding process of evolutionary exploration through genetic sequence space required billions of years to produce an organism complex enough to sit somewhere and wonder why it took so long. The mathematics is not cruel, it is simply indifferent. Random mutation explores the space of possible organisms at a rate constrained by generation times and population sizes. Natural selection filters that exploration based on differential survival, but the space of possible genetic configurations is so vast, and the proportion of configurations that produce highly complex nervous systems is so small, that even with the enormous populations and rapid generation times of microbial life, billions of years are not excessive, they are necessary. We are not the goal of 13.8 billion years of cosmic history. We are a statistical event in it, improbable enough that the conditions for our emergence required the entire age of the universe to assemble, common enough that they assembled at least once in a galaxy of hundreds of billions of stars. What strikes me as the most profound physical reality in all of this is the chain of necessity, not the chain of purpose, necessity. Carbon had to be forged in stellar cores because the Big Bang did not produce it. Rocky planets had to wait for multiple stellar generations because early interstellar gas was too metal poor to form them. Biology had to grind through billions of years of microscopic exploration because the thermodynamics of complexity offers no shortcuts. Each of these links in the chain is physically necessary, and the chain as a whole spans 13.8 billion years, because that is precisely how long the chain is, not one link shorter. When you hold a piece of iron, you are holding an atom whose nucleus was assembled in the final seconds of a dying star hundreds of millions of years before Earth existed, then dispersed across interstellar space, then gravitationally recaptured into the cloud that became our solar system, then concentrated by geological differentiation in the young Earth, then cycled through ocean chemistry, then incorporated into the hemoglobin of every living thing on this planet, and finally delivered to you through an unbroken chain of biology that stretches back 3.5 billion years to the first self-replicating molecules in the early ocean. That chain does not require a purpose to be magnificent. The mathematics of nucleosynthesis and thermodynamics and evolution did not need to be aimed at anything to produce something genuinely astonishing. The clock did not need to know what it was building for the gears to finally align. And the fact that some of those aligned gears are now sophisticated enough to trace the full length of the chain and understand each of its links, that is not the fulfillment of a cosmic plan. It is something far more remarkable. It is matter achieving sufficient organizational complexity to comprehend its own origins. And that comprehension, built from the physics of deep time and stellar death and thermodynamic necessity, is a richer foundation for wonder than any story requiring a waiting universe ever could be.